Welcome everyone, I'm DSP and this is an introduction to the Unix operating system in a module we call Basic Investigation and Discovery. The outline of this module will have to do with computer organization, general primitives and abstractions that the computer and the operating system hold. We're going to talk about the hardware architecture in an abstract level, how the CPU, memory, disk and network fall together. We're going to talk about how the operating system is structured, in a sense how the kernel presents the processes or the files to the userland, and how the shell works in order to tie all these things together and allow us to work with files and processes and use the hardware. We're going to also talk about the security model that the hardware provides, like the rings. We're going to talk more about that, the permissions that you can assign on a file, or the way that you can isolate memory from one process to the other. And then we're going to talk about the forensic process. That means observing the activity and making sense of what is normal activity or like abnormal activity. We're going to talk about how to gather information and what are orders of volatility, which is a metric that we can use to see what should be our priority on what to gather first. We're going to talk about doing either online or offline analysis on the data that we gather, reconstructing timelines. That means like a rough ordering of events and presentation of the events in an ordered way that we can make sense out of them. We're going to talk about the Unix operating system and certain Unix commands that are very useful to know and we will be using throughout this course. Finally, we're going to talk about what hashing is and how to preserve data from a computer system. And finally, we're going to also talk about data carving, which is the process of carving out parts of data from a larger stream of data. Let's just jump right in. So, in a sense, what is forensics? We can say that forensics is a collection of skills and processes that we have in place, and using those we can investigate what is an anomaly, either a natural anomaly, like something is going, something is abnormal in the way a system is executing and we want to find out why, or maybe a man-made anomaly. Someone is causing some potential trouble on a system and we want to see what he's doing and what is the nature of the disturbance they create. Then we would also want to reconstruct timelines. We want to make sense of events and put them in a natural timed order and say, this happened first, then this happened afterwards. And by that we can create a flow of events in time. Then we want to preserve these events and this evidence, but in a way that is free from distortion or bias. And that's very important, because when we start investigating a case, we shouldn't have anything set in stone on what it might have happened, because we're still investigating. We know actually nothing about what has happened. So in order to present an opinion in the end that is truthful, we need to create that truth only out of evidence that we find from that process. The last part that I mentioned here is the formation of an expert's opinion. So we might be called to court to present our opinion on what has happened on a system, and to do that it is important to make note of bullet 3. It needs to be free from any distortion or bias, because when we're presenting our opinion, it might become part of a legal determination, and it is very important when other people's lives are at stake to make sure that whatever we say or whatever opinion we start developing is only grounded in reality and evidence that we have actually seen and measured ourselves. So you see that to do this sort of thing, we need to be able to acquire data efficiently from the computer. And to do that, we need to kind of understand how the computer works internally in certain levels. That's why we start diving a bit deeper on the parts and the interfaces that the computer consists of. So, in a sense, the big picture, we can say that a computer is a collection of independent units working together. And von Neumann had presented his original idea on what a computer can be. He had said that we might have a different unit that controls the flow of execution in a program. It can control if a program is going to go this way or that way, or if it's going to take a branch or not. It might also comprise of an arithmetic and logic unit that might perform certain arithmetic operations. And it might also have registers, which are tiny parts of memory that the computer can utilize to keep something in a way that it can be accessed very quickly. It might also have ways to interact with its environment, either by an input device or an output device that can print stuff for us to see, like a screen. And it might also have like extended memory units that it can write data to and read data from. Like that would be the random access memory or RAM that we kind of know on our computers. So you can see that because certain parts are closely tied together, like for example the control unit as we pictured here with the registers, they are close by. The access time for the control unit to see what is the status of a register can be, and I'm writing here, it can be measured in nanoseconds. What I want to say is that it can be pretty fast. Right now it's nanoseconds, maybe in the future it will be even faster. And we're also mentioning here like certain levels of caches, L1, L2, or L3 caches. These are different levels of memory that are closer or further away from the rest of the CPU, so that the CPU can write data or read data from that memory faster than it would do from the same memory of an order higher cache. So that means that data on an L1 cache can be accessed faster than data than in an L2 cache. If we go down to the random access memory, the RAM of the system, which is outside of the CPU, then these accesses might take tens of nanoseconds, as I mentioned here. Or if we want to access something on the network, then we might go in the microsecond access time, because we might have to talk to our network card to see what is in its own memory. Something we'll realize here is that every subsystem of the computer kinda these days is a computer by itself. So the network card has a memory of itself, the same thing for our graphics card, as you probably know, and maybe even our sound card has a memory of itself. Maybe even the screen that we display data on has some small memory of itself to actually get the data there, accept it, and then do some pre-processing before it renders it on the actual screen. And finally, we can talk about the disks, which are persistent storage, and we can persist our files. That's where the bulk of our data is actually stored, and these can have right now access times in the order of milliseconds. So if we want to take a snapshot of the computer at a given time, we would have to get the status of all these CPU registers, all these caches, the bits that are in our random access memory, whatever data is persisted in the disks, as well as all the individual memories that comprise our network interface cards, our GPUs, and all the other peripherals that our computer has. And we have to state here that certain operating system abstractions that we have, or things like running in a virtual machine, executing our code in a virtual machine or in a container, give extra boundaries in this process, and therefore make it harder for, if executing from within a VM, to access the actual hardware, or if executing within a container to access the actual hardware that the machine is actually executing on. So, moving into what are orders of volatility, we can see that we can imagine that certain things change faster than other things. So data that is stored in registers change faster than data that is stored in the disk. Let's think about that. Every time we load, for example, a text file from the disk and we're starting editing on it, but we're not necessarily saving it back to the disk, right? We might do a lot of changes, like we might change all the instances of the word foo to bar. But this has happened very fast in our editor, and it hasn't necessarily persisted in the disk. Well, this probably has happened initially at certain registers, and then maybe in a certain cache level, maybe in L2 or L3, because the whole file had been brought into a cache if it was small enough. So the changes that we did appeared to have executed very quickly, but that's because they were executed in an environment where the whole environment was pretty ephemeral. Everything was in the cache. It never touched the disk. It never touched the network. So we can start understanding now that certain operations on the computer might be happening in different levels of accessibility for it. Okay, and generally, for the computer to actually operate on something, in the end it needs to bring it up to something that it can address. Like, it has to bring a file from the disk into memory somehow to be able to do something on it, and to be able to actually change a small part of that memory. It probably has to bring it into a cache, and maybe actually even bring it to a register so it can address a word, for example, in that text and do something on it. So by figuring out how quickly something changes, we can start making plans on how important it is to persist it. I mean by that the registers in a computer, since they're changing very fast, if I want to get a status of them, like I actually want to read the status of every register, probably the only way that I can do that is by keeping the computer running and examining the status of every register. If I turn the computer off, just the function of turning off the computer is going to change the status of the registers. The same thing for the caches. Just turning the computer off, issuing the command for the computer to turn off, is going to change the data that is currently in the cache. So if I want to examine the data that's currently in the cache, because it might be super important for me, I have to find some way to do it non-intrusively while the computer is running and without issuing a shutdown command. I have to somehow find a way to examine the memory of the computer without me interfering with the computer. Kind of the same thing happens for the random access memory. I have to find a way to see the status of it without tampering with it, because if I turn off the computer, the random access memory is going to be reset. However, things like the file system are usually persisted. So if there is a file in the computer that I'm interested in, it wouldn't be too bad to turn off the whole computer, because probably the file is going to keep being stored in the file system and I can access it later just by maybe removing the disk drive and examining it at my own location. Now, for things like network operations, we say here that they can be seen in vicina. That means like from a neighborhood. So if I can see what the computer is sending or receiving from another computer, then I can infer what's happening on the computer I'm observing. Let's talk a bit about how the operating system is structured and what interfaces it gives to us. This is an extremely oversimplified picture, and I'm sorry for the crimes I'm going to commit here just presenting it like that, but we have to start at some level of abstraction before we dive deeper in. So we kind of know that an operating system comprises of the kernel and the set of user space programs that come with it. The kernel is just the core of the system that is responsible for talking with certain devices like our disks, and might present a file system for us that we can write and read files in those disks. Or it might give us a way to talk with the rest of the network and interface with a network card. Therefore, it might have a network card driver and a whole set of network protocols that it uses to talk with the rest of the network, like the TCP protocol or the IP protocol or UDP or many other protocols. Then it might also have the scheduler there, which allows us to schedule different processes to run and maybe change very quickly from one to the next, so that they give the illusion that the operating system is actually serving multiple tasks at the same time. We know that this is not happening. We know that at every core, the operating system can execute only one task at a time. But the context switching is happening so fast that it gives the illusion that many tasks are happening at the same time. So I can, for example, listen to my music from my favorite streaming service, and at the same time browse the internet and also edit a file with my favorite text editor, and everything seems like it's happening at the same time. However, the scheduler is what's doing the magic here, and it's really quickly context switching between all these tasks. But the human that is observing the system thinks like they are all happening at the same time for our human time scale. We have other parts like the memory manager that is managing what memory is going to be presented to each process and its user. And also we have a set of, as I said in the beginning, userland programs. These userland programs use the abstractions provided by the kernel, and I mean like things like processes, files, or sockets. Sockets are just special files that instead of writing the data to the disk, they can write the data over a network connection. And these abstractions allow that are provided by the kernel allow interesting programs to be written, because they take away a lot of the pain of actually talking to the actual disk drive or talking to the actual network card. They abstract it in a way that is useful for more complex programs to be written with. Like you might say, I just want to connect to www.google.com and get that result of that HTTP GET request. Well, abstractions like the socket or the TCP/IP network stack allow you to write a program that makes what we just said small enough to be executed, so that you can build complexity without having to deal with actually ferrying memory buffers and packets directly from and to the network card or the disk. Now, for that to happen, the kernel and libraries that we use provide interfaces to interact with. these interfaces are these boundaries that will be able to collect forensic data. And I'm starting to hint here on the need of having security controls that in these interfaces. Because, for example, let's say your text editor can load a file that you have into memory. Would, on a multi-user system, would it be acceptable for some other user to access your loaded file in memory and change it? Probably not, because it's a file loaded by you. And intuitively, we think that if we load a file in memory and start operating on it, we wouldn't want some random other user to be able to mess with our data. So starting talking a bit about security, which is a vast subject, and we really cannot cover not even a tiny percentage of it here. We'll just try to be pretty vague and get just what we need out of that subject. So we can imagine security as a set of, again, processes that we put in the system in order to control certain things and allow us to have certain guarantees. A famous way of presenting the impacts that a secure system or a non-secure system can have is the CIA triad. Thinking about the service that we're providing and saying, is this service going to be, in a sense, confidential? This is the C of the CIA triad, the confidentiality. Or is it going to have an integrity? Like, will people be able to mess with the integrity of the data in the service that we're providing? That would be the I, integrity. Or is it going to be available for us to use it? Because if someone can crash it very easily, then maybe it won't be available for us to use it, and therefore it won't be useful. So this is just one way of presenting the potential impact of that security can have in a system, the CIA triad. But there are more ways of examining a complex system. Now, as we said in the previous example, we might have multiple users that are executing on the same system. And in the beginning, when, let's say, computers became a commodity, they would only have one system executing at any given time. But then people found the need that they would like more users to be present at the same computer at all times, and every user should have their own files, and every user should be able to run their own set of processes, maybe have different users executing at the same time together. So a certain set of security controls needed to be created around this idea. So from the 70s on, we started having the idea of multi-user systems, and then security controls need to be created so that they isolate one user from another. Then from the mid-80s, early 90s, networks started becoming more popular, and all the computers starting being part of larger networks. So now every executing computer node, every part of a network, should be able to be kind of isolated from other nodes in that network, because you wouldn't want, for example, another completely different node in the network to access your computer and execute commands on it. At least you don't want that most of the time. Maybe in some cases you would want that, but most of the time that is not desirable. So we started having like this multi-node way idea of securing systems. Like, we need to secure our node against other nodes. And from, in the last 20 years or so, we have seen that we're using certain completely isolated services on the internet. Like, for example, I might want to log in to my streaming, my music streaming account, on service A, and this might ask for me, it might ask for my whatever, let's say Google password. Like you might need my Google account to log in on that a streaming service account. Well, let's say I provide, I log in with my Google account on that service. I wouldn't necessarily expect that now this service might have access to my Gmail data, right? That would be pretty bizarre. Like I wouldn't expect, for example, Spotify to have access to my Gmail data. In that sense, I have multiple services working together. One service, for example, in this case, Google, is providing some sort of identity provider, and provides a username for me and a way to authenticate if I have logged in. Then another service, for example here Spotify, might ask for me to authenticate through Google, but if I do that, I wouldn't necessarily expect that now Spotify would have access to my Gmail data, right? There needs to be some sort of isolation here, and that's what I mean by multi-service isolation. Now, as you can imagine, these systems grow more and more complex every day, and even right now, these systems are almost infinitely complex, and no one can manage to visualize in their mind exactly what is happening in these systems from the level of for example, Spotify service requesting some sort of JWT token, down to the program issuing a system call and writing on the network interface card. It's a really complex system, and really complex systems are very hard to keep secure. So we do our best in terms of the hardware, the software, and also the human factor here to try to keep these systems secure in the best way possible. But we also need to remember that because the systems are so complex, there are going to be major failure modes that we should be prepared to see in our day-to-day life. So let's talk a bit about how hardware security, and we're just going to give a very vague hint here. We're going to talk more about memory security in our memory forensics module, but this is just a very high level picture. You can see a graphic on the right side of the image here. We see that the hardware provides certain rings of execution. Things can execute in one of these rings or another, and depending on what we have marked here, depending on how far out you are, like on this ring, you're less privileged than if you're like on the center of the circle, on ring 0, for example, and we say here that the kernel is executing on ring 0. But what does that mean? What are the actual implementation details that go with executing from one ring to another? Well, this is a very, very, very complex topic, and again, please excuse me that I'm just brushing over it. Like I'm just not presenting a very large amount of knowledge here. I just have to keep it abstract enough so that you can get a rough idea. And please excuse me for the generalizations I make and the mistakes I might have in what I'm going to say. So again, we said here that the applications might execute outside on ring 3, but the kernel executes inside on ring 0. One way to think of this is that the CPU allows us to address memory. And what I'm going to hint at here is that the way that you can address memory when you're on ring 0, while the way that you can address memory while you're on ring 3 are different. In a sense, we can think that maybe that when you're in ring 0 and you address memory, you can address potentially all the memory on the computer in a very direct way, while when you're outside on ring 3, you address memory through a mechanism that kinda isolates you from what other application might be executing on ring 3. Okay, I hope that kinda makes some sense. And when we have x64 CPU and x86 64 like CPU, we kind of know that an x64 CPU has 64 bits worth of addressing. That's what we say. So you expect that you'd have 2 to the 64 possible addresses for memory address that you can work on at any given time. That's not really true though, because a computer does not access a byte individually or a bit individually. It would probably does what we call paging. So a paging means that the smallest quantum of memory access that you can do has to be a whole page. And in this case, traditionally a page, let's say, it's defined as being a 4 kilobyte page. That means at any given time you can access 4 kilobytes of sequential physical memory. Okay, so when you access anything inside that area, the system just cares that it is in that 4 kilobyte range, and it always brings into the cache or writes back into the disk or flashes into the cache all that complete 4 kilobyte page. That allows the system to save some space, right? Because now if you address everything as your smaller quantum is a 4 kilobyte page, then you can save some space, because you don't really need to have every address, right? You only need to have every start of a 4 kilobyte page, and then whatever else is happening in there, well, you don't care. You're just bringing that whole 4 kilobyte page in, or you're writing that whole 4 kilobyte page back. But then you don't care. You will never, on that level of abstraction, you will never address something in that 4 kilobyte page. So that part of the system that we are talking about now, the MMU, the memory management unit, only goes up to the 4 kilobyte page, for example, size. Therefore, it can save some bits. That it never looks into them. Other things look into the bits in a 4 kilobyte page, for example, your application. By saving these bits, although it started with 2 to the 64 bits, it can now start working with less. So it can use only just 2 to the 48, for example, bits in a modern Unix operating system. Only these are used for addressing, and the rest bits can be used for other purposes. Okay, so if we can split everything in these types of pages, and we also have free bits further up that we can use to write more information on them, maybe we can write some information there on if, for example, this page can be writable, or just only writable, or only executable, or, for example, maybe it can be both writable and executable in some cases if we want that sort of thing. Or maybe we can have another type of permission here on if that page should be readable. Maybe some page shouldn't be readable by some parts of the system. So we can use these extra bits that we have saved here from the 64 down to the 48 to start writing certain types of security relevant or generally operating system relevant data there. In the case that a modern x84 CPU accesses a page, here's this implementation detail. It will first access the control register 3, which is CR3. Then it's going to go from there. This is going to have a certain value. So you can imagine in CR3, this value will index into a table of many more addresses. Okay. From that table, we'll take an entry of that table as an address, and then we're going to have another table there. And that table, in this case, is called page map level 4. And we're going to get one position in that table that's going to have a pointer to another table, and we're going to keep addressing from level 4 all the way down to level 1, where we're going to get eventually an address, and that address is going to be the start of some 4 kilobyte sequential set of memory. That's going to be our page that our application is going to be using. So you can imagine that by following down, this path of we first access this register and then go into a table and we pick an entry on that table, then we pick another table, we go on an entry of that table, and then from there another table, blah blah, and we end up in a page. We can create a good enough isolation. For example, we might say that, for example, all addresses between this index and that index of that table belong to that process only. And for example, that process, if it tries to touch any other index that's in that table that's not allowed, it automatically crashes. If we do something like that, then we could ensure that processes could have a completely isolated view of the memory they access. Now, to talk to devices, we kind of hinted before, we might need to do what's called a direct memory access. A direct memory access means accessing a part of memory that is kind of shared by both the operating system and the device. Whenever we do a write on that part of memory, then the device will become aware of that, and that memory is going to be kind of read by the device as if that memory was on the device, and the device is going to do something based on what we wrote there. For example, a very simple view there is like, let's say we have a sound card. It has a certain map of DMA, like a part of memory that whatever we write there, if it is in the WAV form, like a waveform, if it is kind of like an analog signal, in terms of like volume levels and pitch levels and maybe musical tonality, whatever we write there is directly becoming a sound played on the speakers, on the output of the sound card. So if we start writing there a waveform that kind of can be like a sinus, for example, then we're going to hear a sinus-like sound coming out of the speakers, okay, instantly, because we wrote in that part of memory. We have some memory that we can write some data on. This is going to be directly rendered into an action from the sound card, and it's going to become a sound that we hear on the speakers. The same thing happens for the graphics processing unit, the GPU, and all the other peripherals that we might have. They kind of use some sort of DMA, direct memory access. Now, older CPUs like the x86 had a similar idea to this dance that we saw here, jumping from CR3 to PML4 to blah blah to some page. It kind of had what's called a segment register, and depending on the value of that segment register, it would pick which segment of the physical memory to actually access to do something. But this has kind of been phased out on x64. Now, we talked about having certain free bits that you can store extra information there. Certain architectures like ARM take that a step further, and in these bits they might add more security controls. Like they might give you a way in these bits to have your abstract tag on what this part of memory means to your application. So let's say you give out like for example 3 bits worth of memory there, like for a tag. So you can define 2 to the 3, for example, possible types of tags there. You might say, oh, this block of memory means this tag for my application, that block of memory means that tag for my application. And what can that enable? This way we can say that certain memory regions have that extra information that we put there, that is a certain tag. And if we make that part of memory non-accessible to normal users, so when the program is executed, it's not allowed to touch these tags, because maybe what I mentioned here, these tags could be persisted in a shadow part of the memory that's not writable while the program is executed. It's set in stone when the program is starting. Well, if you try a memory corruption primitive like a buffer overflow that it allows you to write past the memory that you're typically allowed to write on and corrupt the data structures that are around that memory, this sort of mechanism of that had allowed the programmer to put a tag into that memory space would probably catch that because you're not able to write onto that tag space, and it would detect that this memory that you're writing into now has a changed tag from what it should be, and it would stop the execution of the program. This is a very vague presentation of what a tagged pointer defense mechanism looks like, but you can read more about it. So there are many more security mechanisms that come into play. Here on the right we show a graphic of what the virtual memory of a process can look like, how this is actually implemented when we have the physical memory. And that's because every program that starts executing is given by the kernel. It's given, let's say, infinite free memory to execute on, and the program doesn't really care about how much memory is in the system, or it doesn't know any of these constraints. It thinks it has as much memory as it might need. Now, if that program starts allocating too much memory, then of course, if we have a system that only has, for example, 16 gigabytes of RAM, then someone is going to allocate all the available memory to it, and it should crash. So eventually, of course, there's not unlimited memory in the system. And that memory that is presented to it, it's not necessarily sequential, because in physical memory, as we see, it might be overlaid in many different ways, and there might be there's definitely memory of other processes interleaved in there. However, the abstraction given to the program is very simple. It's like, you start executing here, and you have all that available as your memory that you can use as scratchpad, for example. Allocate as much as you want. That's a very useful abstraction because it makes programming simple. We don't have to deal in our program with, does this computer have enough RAM to execute on? No. Technically, most of the time, we don't care about it. We just start allocating stuff. Okay, worst case, the kernel is going to notify us that, sorry, I ran out of memory here for some reason. Now, in terms of other security controls, there can be many different abstractions that are into play, and all of them can happen usually at the same time. So, for example, in Cisco IOS, an operating system that runs on network routers and switches, there is this idea of the configuration mode. So until you put your system on the configuration mode, then you can't really change any important parameter of it. To enter the configuration mode, you might need to enter the admin password, right? So until you do set config blah blah, it just doesn't accept any change in any sensitive variable. So that's sort of a security control here, right? It enforces you to have the admin password to enter the configuration mode and alter some important variable. Also, we talked about how a system can have multiple users. Well, most Unix systems also allowed a mode where the system runs as a single user system. So when you do that, many of the multi-user security controls are just not there, because you might be executing the system in a simpler way, like where there's only a single user, and we don't even need to consider the other types of security controls. We talked about virtual memory and how it segments real memory and presents it as a sequential resource. We talked about users having different permissions to access different parts of the system. Kind of here we start talking about files. Files might be owned by a user, and depending on who is the owner, the owner might have a certain permission to read, write, or execute the file, but also other users than the owner might also have permissions to read, write, or execute the file. And if you kind of think about it, this is kind of a complete set of what types of operations you can do on a file. But there are also certain other subsystems like capabilities on a program. So for example, we might have a program that we give it the capability to talk to the network. We might enable it to talk to the network card and to the network interface. That might be a capability here. Capabilities are kind of more fine-grained permissions. You can see them these days, like for example, when you issue a GitHub token, it might ask you, okay, what do you want to do with this GitHub token? Do you want to access all your repositories? Do you want to be able to set your user identity, or change your password using this token? So you give certain capabilities to the token, and these are fine-grained capabilities, and by that you might protect it more. So you might issue a token that's not really trusted. If someone is trying to do something nefarious with that token, they might steal it. Well, in the worst case, they won't be able to, for example, gain access to your data and issue more tokens that can do more damage. They might only be able to, at the worst case, for example, delete all your repositories, which sounds pretty bad. But okay, in a sense, it might be less bad than deleting your whole GitHub account, for example. Now there are other operating systems like OpenBSD, which have devised even more interesting security mechanisms, like pledge here. You as a programmer might say that, okay, I'm writing this program, and this program is not allowed to touch this and that subsystem. It's only going to be allowed to touch, for example, the disk or the sound subsystem, because I'm just a program that plays MP3 here, and I'm not going to ever touch your graphics card, for example, because I don't care about it. So by pledging what type of subsystem you're accessing, you're putting that information in the executable when it's created. So the kernel then, when it runs your program, if it sees your program trying to access a subsystem that you have not pledged there to touch, then it's going to stop the execution of the program. It's a very efficient mechanism. And of course, there are more many different security control knobs that you can turn on the system. Here we're going to talk a bit about the Unix operating system and certain commands that we're going to be using to interact with it. I'm going to pause the video and continue on another one.